evening. And without further ado, I will be starting the afternoon session off with a presentation by Simon Wang. Simon Wang is an assistant professor of the Climate Program, Department of Plant, Soils, and Climate at Utah State University. He's also the assistant director of the Utah Climate Center, and his research areas cover climate dynamics, prediction, and applications. So let's give a warm round of applause for Simon.
Thank you. Can you hear me okay? Well, thanks to Darren and then Justin and Marcella for giving me this chance. I'm not a forest ecologist. I'm not a biologist. I know very little about ecosystems. I'm just a climate guy. Given this chance, I thought that since I'm a replacement, I might be saying something more fun and then getting outside the box a little bit, especially during these after lunch hours. So I'll be just talking about climate cycles or climate oscillations that you may have seen in your area of research, the data you collect. That means repetitive dryness or wetness, or growth or decay of something that's going on there. We know that in the West, trees tells a lot of story about wet and dry cycles from the tree rings. And in our region, in the Intermountain West, we have a very distinct cycles that has not been known. And believe it or not, was very little research done about what is caused about that. We know a lot about El Nino and La Nina, for example, but those are not the major cause to our dominant climate cycles. What are the climate cycles? So I only ask you to understand one thing first, so we can move on. In the climate data analysis business, there's one function we frequently use. It's called EOF, or it's pretty much like a principal component analysis. So as long as you get this idea, we're good. Okay? So imagine a row of ducks waiting to jump into water. If you throw something like an EOF into this group, then eventually the program tells you something like this. You have the first leading mode, 60%, second leading mode, and etc., some smaller modes, right? So you can do the same thing. Now you're seeing the grid points of the climate data derived from tree rings. So this is a data set compiled by Columbia University. It's a tree ring-based drought severity index across North America, okay? So if you throw this EOF into this, and in this case, I'm showing you more than 300 years of records. This is the second leading mode. So you now see wet and dry alternating, okay, with Utah in between, that we know that is caused by El Nino or La Nina. Or if you talk about decadal cycles, the PDO, Pacific Decadal Oscillations, they form very similar structures, okay? So we know that. But this is the actual first mode. And it comprises more than half of what we know as the El Nino influence in the second mode. What is that? What is causing this? Nobody knows. But this is, again, the very important mode. Whenever you see the wet-dry cycles, you can see that the areas of influence is surrounding the heart of the Intermountain West, okay? Well, we have a gigantic rain gauge helping us to record these wet and dry cycles. That is the Great Salt Lake. Then we have the lake level data going back for 150 years. You can see that the lake level has experienced these up and downs, very low frequency. This is annual raw data. It's not filtering at all. So the lake is actually documenting the predominant drought cycles, because every time the lake level decreased, there was a drought, big and small, okay? Well, if you superimpose with the drought severity index and filter it by the prominent multi-decadal time scale, you start to see that the trough of that PDSI, which is drought, coincide very well with the lake level fluctuations. So that's our climate regime in the center of the Intermountain West, okay? What is the forcing behind that? Well, the majority of climate forcing affecting us came from the Pacific, so you naturally link it to El Nino, La Nina, but in this case, it's not. It is something less known compared to PDO. It's called interdecadal Pacific oscillations. So they fluctuate in a slow-moving manner, and then after they reach a transition point, not extreme warm or extreme cold, they start to influence the precipitation regimes here in the Intermountain West. And that later on, through hydrological process, translate into the great solar elevations. So the process actually takes many years. You can see from the peak of that, propagating to your drought regions, propagating to the Great Salt Lake, okay? And that caused an initial misunderstanding of a direct one-to-one response, which dynamically and hydrologically, it's impossible. So we actually have go through this transition phase, a fancy term called teleconnection, that from the IPO to affect our multi-decadal climate cycles here. Okay, we have published these results, and then we try to make forecasts out of that. So really, this is the climate regime or drought cycles that I really want to call attention upon you, the audience here, because we have found that the variance here of these drought cycles outweigh a lot of the known oscillations like ENSO, El Nino, La Nina, and they are independent from the Pacific Northwest. They are somewhat independent from the Southwest United States. Okay. So what's the impact of these unknown climate cycles? Well, if you are a climatologist, or if you need to do anything about climate in the future, you need climate forecast. There has been an operational climate prediction output from NOAA. I hope they reopen today, to produce the so-called seasonal climate forecasting. The definition of seasonal climate forecasting ranges from 2 weeks all the way to 6 months. And if you talk about ENSO, there's sometimes 9 months or a year. But pretty much 6 months. That's the seasonal prediction. Like right now, what's anticipating if we are going to have a wet or dry winter. That's seasonal prediction. And there's a unique product of that. But because of this knowledge or lack of it, Utah and the central part of Intermountain West is situated in this no man's land. The jargon for climate forecasting is called EC, equal chances. It's a very fancy way to tell you, I don't know. Because there's 50-50%, you can be either way, okay? And we are also situated in this, no one knows why it is causing these cycles, okay? So the lack of knowledge directly reflects to the lack of model performance. The two combined actually degrade our climate prediction skill dramatically. I have a solid proof. This is the grid point model product of seasonal prediction. So they use the model forecast data in the past to verify with observations, and then you can get a skill, right? This model comes from actually an ensemble of many different models, from NOAA to best European models, NASA models, and NOAA forecast model, research models, and National Center for Atmospheric Research in Boulder, Colorado. They are the world's leading institute for atmospheric research and climate model developing. Or you may think that as 18 models, basically. So what they do is, over this region, over that region, God bless them, they have very good skills. So they actually benefit from model results. Well, how about our regions here? It means climatology, or assuming every year is the same, actually outperform all those models. So that simply means it's better off you read just this for next winter. So this is state-of-the-art global climate prediction models, okay? So what does it have anything to do with our future projections? Now, if you have heard about CMIP3, you know there's the last generation of models producing the United Nations IPCC climate report. If you haven't heard about that, don't worry about that. Previous models, previous version, okay? What you are seeing is the annual precipitation projection or change for the middle of century from now on. That's assuming it's 2050. So you can see that Utah or Intermountain West is situated again in this transition zone. So here is drier, here is wetter. That's our forecast climate in the future. So now these models have evolved. People are adding resolutions, adding those different physics. This is the current one, just released, I think a couple weeks ago, CMIT-5, the latest generation of models. Again, the same prediction for the middle of century. Now you can see that Utah has some sort of wet future compared to older ones. For climate model developers, and this is no secret, we know the fact that older models do not necessarily, are not necessarily worse than the earlier models. Because every time when you introduce something new, more modern, it affects everything else. Imagine you are paving the carpet, right? You put this part down and that part pop up. And that is model bias. It happens. So sometimes the first step for modelers is to compare the two projections. So if you compare the two, this is the uncertainty that you get. And then guess what? Utah is here with the most uncertainty for precipitations. Now, this is way beyond seasonal prediction. This is the middle of century. And you can refer that to end of century predictions. So if you want to run your ecological models, forestry models, using this kind of data, you need to be very careful about this bias present in these multi-model ensembles, okay? What does that have any impact directly? Well, the most direct impact, given what we have been doing, is related to water resource. So now you're seeing the water supply data from Colorado River. So there has been the water supply in the past, and water use has come up, and then the intercept, meaning that, well, we don't have enough water for the future, and this is the prediction they make, okay? When you combine all those 20, 30 models, they pretty much give you a straight line with uncertainties like that. There's no way the models can capture all these decadal cycles, drought cycles, okay? But we have done research, for example, by knowing what is the climatic forcing affecting the Great Salt Lake elevation, and you can see first how well Colorado River water supply coincide with the Great Salt Lake elevation change. We're surprised to see this, and better yet, because we capture these dominant cycles, we were able to predict that, and that is the becoming operational predictions that we're trying to make there from the Utah Climate Center. Okay. So what's the cure? What can we do about it? Well, from the climate modelers or climate researchers' perspective, there are only two ways we can do. One is to improve the models, but improve from what? Okay, improve from better knowledge, that you know what is the forcing, so you can tell the models to respond better to the part of the Pacific Ocean, for example, where the teleconnection energy should come from, okay? We also need more local research, and this is the modern data. You can see this is precipitation anomaly for 2011. Well, wet and dry, but we have a lot of big details here, which matters a lot to regional water managers and to, I guess, individual forest plots, for example. But this is the current triggering drought grids. You can see the resolution is pretty coarse. And if you plot them with just the map, you can see the deficiency of a coarse resolution will give you really not much, right? But we have tried here. I'll introduce you more and more what this data set is about. Again, a triggering data set is derived from the Forest Inventory Analysis, FIA. It's called the nation's forest census. And we have done over Utah from these 3 samples, and here are some statistics of the number of years that individual tree crops will record. You can see average 150, sometimes they are over 250 or even 300 years old. And only for these 2 species, and you can see these are the plot numbers that you have probably sufficient amount of data going back to 1750 or 1800s. So that gives us more than twice more power in terms of time resolution and spatial resolution to understand the local climate effect, okay? So we have done some analysis for that, just to make sure that the FIA data, the triggering data, does represent climate. So again, remember the EOF ducts. If you throw the data set, in this case, projected into the 0.5 degree resolution, you can see this grid. And then this is the time series you get. The blue line is FIA from the triggering data, the new triggering data, and PDSI is the 4 grid points from a different type, totally independent tree-ring-derived drought indices. And you can see how well they fit. I think the correlation is somehow about 0.8, okay? So this is a sanity check because you are comparing between blue and red, two very independent data sets. And yet they tell you this general agreement about the drought variability here in Utah, okay? So with that in mind, we can now start to explore further details, right? Again, throw in this UF ducts analysis into first mode, second mode, third mode, fourth mode. You can have a lot more. This is their time series. You can use this time series to regress back precipitation with high resolution precipitation data. You can see this is a water year precept. Just see how they compare each other. The general pattern is there. It has a very good spatial agreement, meaning that our tree-ring data here, when they are crawled, they didn't have any climate reconstruction in mind. They simply crawl it. But then you can see they do reflect climate variability in the general senses. Like the leeward, the windward side of the mountain, the lee side of the mountain. It's quite interesting. You can compare with existing PDSI data. So you can see the dramatically increased details from this to that, okay? And there are something more you can do. So this is a very complicated plot, but essentially what we are doing is you see those black dots, those are individual tree cores. So you use the chronology, tree-ring time series, to correlate with local precipitation. We use gridded data, okay? So you can see 0.8 here means that all these trees respond very well with local precipitation. And in this case, it's the water year precipitation. You can see along the Wasatch Range, the correlation was pretty high, and it's all significant, okay? And with that, I've been thinking next, how can you use this information to reconstruct our climate? The first thing we had in mind is snow. So we have this wonderful snow-tail data, but they are only as long as 30 years. Can we construct a 300-year snow climatology? Would that help? Well, I believe so. And then I have my students now working on this, trying to reconstruct them back. And we can also now try to increase the drought resolution over the state and over the region. What you are seeing now is the satellite-derived drought index. And we are hoping that the density of the tree-ring data can give us as good as the resolution, or nearly as good, okay? And there are some other fun things you can do. In this case, I should have Justin present that. But, well, recall, we have these drought cycles recorded by the Great Salt Lake elevation, right? So if you correlate with the tendency or the rate of change of the Great Salt Lake elevation upon those FIA tree-ring data, it can give you these very high resolution correlations, and then you can go there pretty much fishing for signals. So these are the 4 regions, for example, that we found. It's a little bit counterintuitive, where the Great Salt Lake respond the most, okay? It's actually in all these regions. And ideally, if you couple with those regions, you go there, you can tree for the cores. You can call for the trees, sorry. And then get more sample of data, and you can construct them back. So this is from Justin. You can see now it's the Great Salt Lake level reconstruction back to before 1500. And that gives us a lot of statistical power to further understand climate cycles here, okay? So we have data, of course, beyond Utah. And the study that have been done, published by DeRose et al., use only these 2 species, and these are the map you're seeing from these 2 species. But in Utah alone, and Justin told me, we have more than 3,000 cores that you can process. That is the resolution you'll be seeing. And you can compare that to existing data set. Station records, this ITRDB stands for International Tree-ring Data Bank. It's pathetic, it's on 3 points here. Okay, compare with that. And it's actually much denser than the station records, and of course, much longer. Okay. So just put in a summary that this is the conventional way of crawling trees. You go out and you find the sweet spot and the best tree species. Our way is kind of like you go out, do everything, and then you get everything, and you can sort it out later, right? So this is the difference in terms of spatial coverage. We're hoping this can provide everyone with not only climate data, but ecological data that you can use, elevation, species, and all other things. So now this is the full potential of the FIA data. Of course, this is just dream so far because it's probably take decades to process all this data. But this is the resolution you'll be seeing. And I just quickly went through the difference between our data or the FIA data with the conventional dendrochronology. And you can just read through them. And basically, they are different. But we're hoping that this data can support the conventional dendrochronology, and to make their science better. And of course, we want to come back to use this data and try to explore our climate variability and the lack of forecast skill problems here. And finally, I want to introduce you the hero of this FIA data. It's John Shaw and Justin, because they really rescued this data from being thrown away about 5 years ago. Okay, so this is just some reference about climate cycles. We have a free online chapter and book. If you are interested in Intermountain West climate, you're welcome to take a look. With that, thank you.
Minutes for questions before the next speaker starts.
Anything to say, Justin?
Good job.
I should put this back. Any FIA training questions, please refer to Justin. Yes, please.
So Simon, a lot of the talks that we've heard this morning talked about climate change and drought and leading to more fire and more insect outbreaks. If we really think about a warmer, wetter place, how does that change that? That might not be the best question for you, but maybe someone else.
You mean what to reconcile between the projections? Well, it's great.
Warmer and wetter rather than warmer and drier.
Yes. We are getting wetter, actually. The problem is the wet region. So you have the rain gauge, the accumulation probably tell you it's getting more and more, slightly. But in reality, if you really look at the data, it comes with more extremeness and longer, not duration, but the interval. So once it rains hard, and then it stops. And the next time it rains hard. So rather than having maybe 3-4 rain events per month, you are having maybe 2, but they sum up with more precip. What does that tell you? It's getting more extremes. So in between, the evaporation with higher temperature actually causes it to dry, the air to dry faster. But then when you comes with these big rainfalls, and you probably lose all the water, most of the waters, rather than a consecutive rain event. We have found that throughout the records for the past 60 years. Yes.
A couple of years ago, or 3 years ago, I listened to this message, and I guess it would be a couple models ago. They were talking about southwest and southern Utah being sort of warmer, drier, and northwest being more variability. And I'm not quite clear if you're saying that message has changed, or we just have more data and we're more confused now.
Well, yes, more confused is the first thing popping in my mind. But I guess you are referring to really this. So, yep, that's true. So you're saying is, yes, before we're saying the southern Utah getting drier, northern Utah getting wetter, and that has changed. So if you ask anyone which model should you believe, I really don't know. Yes.
Slide there said more confusion.
Yes. So that means uncertainty. This means, basically this spot means where models has the most severe uncertainty. So I'm not telling you, and I really shouldn't, which one to believe. I guess I believe my own model if I'm to run that. But I'm just saying that each set, so remember this, each set came from at least 22 models, 22 around the world, okay? And not just the 22 models. These came from each model running for 10 times. So you're actually having something more than 200 runs. So they put out its ensemble mean, hoping that all those signals can cancel out, eventually leave you those climate change signals. They did it for the same thing here, same amount of models, and yet they have changed. That actually tells you only one thing, that this region, the climate in this region is very difficult to simulate, so it becomes very sensitive.
And this may be sort of an ignorant question, but is it possible to have too much data to the point, and I just don't know, where you at least too many overlapping models and too much uncertainty?
I totally agree with you. I would really agree with you. Because I'm a firm believer that we should focus on one best performing models rather than putting all the models together. So let me tell you this, I guess because I shift to Mac, so it's not recording, right? In this CMIS 5, CMIS 3, because this is UN effort, and there are some models that if you ever look at the data, you know they are useless. They're just bad models. However, they are the models representing that country. And that country wants part of this IPCC, so they put this model in. And as a report forming, you cannot exclude models like that. So the easiest way is to put everything into the soup. And that is what you get. So what you're seeing actually is good models' performance being masked out by bad models' performance.
Just a clarification question. The middle prediction, is that mostly focusing on precipitation? No, back.
Yes, I know.
Yeah. Is it mostly focusing on precipitation? And if so, what would it look like if temperature were taken into account?
Temperature actually are more agreeable among models. Temperature, yes. Oh, how would they?
How they interact. If you've got increasing temperature and an expectation of some increasing precipitation.
To give you a quick answer, I don't have data yet, but you have two things to consider. One is increased moisture with higher temperature. That means you have more moisture holding in the air. But looking at the data in the past, we found out, as I answered to Chris' question, that you have actually more extreme events, but longer dry spells. So that is the possible scenario, and I believe it will be the future trend that we'll be seeing. So you do have more rain, more moisture, not necessarily more rain, but more moisture holding in the air. So that is dangerous things. That is what led to the Colorado flooding. When there's a northerly storm coming in, they rain hard. Yes.
The triggering data is sort of synthesizes temperature and precipitation, particularly soil moisture, which is not necessarily directly correlated with the timing and amount of precipitation. There are times in the past that have been suggested, such as the medieval warm period, that perhaps things were warmer and in some places at least wetter during some seasons. Have you taken advantage of the opportunity to look at any, what the tree ring record looks like for those periods of time that were possibly warmer and wetter, and to see if those tree ring records make sense?
That's a great question. It has been repeatedly done within the conventional dendrochronology. Every time they publish a paper, they have to address more or less the kind of problems that you mentioned. We haven't done that in the FIA. What we did in publishing the paper is a proof of concept, only answering one question. Does FIA, when called without the mindset of dendroclimatology, replicate your climate? And the answer is yes. But how do they respond to, how different species respond to different moisture or temperature criteria or soil moisture? Do they have a lag? We haven't done that yet, but you can see there's a lot of potential it can do. We publish the data online, and the data source is along with the paper. It's online now, so if you are interested, please go take a look. Yes, sir.
So going back to this point here, Are you saying that we shouldn't have any more confidence in the findings and conclusions of the AR5 than we had in AR4 or 3?
I should say probably take it with caution. Because you are seeing my purpose here is to tell you models disagree the most in this particular region. What does that mean? That means you have more uncertainty to deal with. So if you want to go with the conventional multi-model mean spaghetti plot approach, now that means you have to change. If you have formed your report 5 years ago, well, that means you have to change it right now, right? Well, how about 5 years later? You have to change it again. So you can follow their approach, or you can support or develop a new approach to get a better feeling about climate projections in our region. That's only I can say. Thank you, Simon. Thank you.